Thank you for the introduction. Thank you everybody again for being here. Welcome to everybody who's new. So this is part two of the basic traffic models and traffic waves. So let me start out by giving a quick recap what we had talked about in part one. So we discussed different traffic models. We talked about the fundamental diagram of traffic flow. So you measure the flow rate of cars and plot it versus the density and get these data points, and then different functions that could be put in the middle, but also acknowledge that real data, while they're a nice functional relationship in the free flow regime, exhibit this spread that is very characteristic whenever you have congested flow. Then we talked about models. Specifically, we derived macroscopic traffic models, so traffic models that are formulated in these variables, density and flow rate, so the macroscopic vehicles, not the vehicle-centric microscopic descriptions. And we ended up, particularly at the Lytle-Witham-Richards model, so the LWR model, rho t plus rho u of rho times u of rho x is equal to 0. So the continuity equation where one assumes a functional relationship between the speed and the density, and therefore gets a scalar hyperbolic conservation law. We saw in discussing the solution methods for these scalar hyperbolic conservation laws that these models develop sharpening of profiles when you have an upward gradient in the density. So it develops shocks, discontinuities. We discussed the mathematical need to make sense of this concept of solutions that involve traveling discontinuities, shocks that are idealizations of very thin zones. Here, a braking zone, a wave of brake lights at the upstream end of a traffic jam, and found the conditions, in particular the shock speed given by the Rankine-Ganeur condition is the jump in fluxes divided by the jump in densities, and that has the interpretation in the fundamental diagram is just the slope of the secant line that connects these two states. And we finished by seeing just in a simulation that it produces this nice sharpening of the upstream ends. We see these shocks. We see the flattening of the profile when we have that the density goes down as we drive along. But we also saw that this does not, by construction, describe any spread here, because you have a direct relationship between flow rate and density. So you can pick one curve, but you cannot represent the spread. And we also saw that this cannot model phenomena that are seen on real roads, for example, instabilities and phantom traffic jams, where you may start out with a uniform flow, perturb it a little bit, and then actually get traffic states that look very differently, that grow out of small instabilities and get, for example, traveling waves like stop-and-go traffic waves. So these phenomena are real in reality. And one needs, of course, to think about how can one generalize the model framework to capture these phenomena. One answer to this is that this can be done by second-order models. So I want to highlight this a little bit. So second-order models essentially means you have a 2x2 system of equations. Sometimes people add viscosity terms here. That doesn't fundamentally change the capabilities of the model in a big picture sense. In fact, these solutions can be rationalized as limits of vanishing viscosity. But I'm going to focus only on the inviscid models, so models that are only first-order derivatives here, so 2x2 systems of first-order derivatives, so specifically hyperbolic conservation laws. So again, there is a theory of these systems of hyperbolic conservation laws out there. In particular, one can understand that every term that involves spatial derivatives can be written in this quasi-linear form with a Jacobian matrix in front here, and the eigenvalues of this matrix are required to always be real. Then the system is hyperbolic, and if they're really distinct, it's called strictly hyperbolic, and that implies that the model is well posed, so that you don't get crazy stuff happening, and the solutions can be made mathematical sense of. So any problem that you define properly with proper boundary conditions has a unique solution that also depends continuously on the data, and that can be made suitable sense of. Now, so there's a hyperbolic part here, and then some models have a relaxation term here. So again, to rationalize this, this here is just, the first equation is just continuity conservation of mass, right? Conservation of vehicles. We discussed this in part 1. And then ut plus ux, that is the vehicle acceleration. So that is the acceleration in a moving frame of reference, as one can easily check by the chain rule. And then forget this p term for a moment. This here means that I still have a function u of rho, but instead of just prescribing that capital U of rho is equal to the actual velocity u, I now say the small velocity u relaxes in time on a time scale tau towards that now desired velocity function capital U of rho. So it's a very natural generalization. I put in essentially a relaxation towards this term. And intuitively, one could even think if tau gets smaller and smaller, this term gets stronger and stronger, and you would actually relax towards the first order solution. There's also something added like a traffic pressure. Here, I've written the traffic pressure as it was done in the classical second order model by Payne and Witham, proposed already in the 1970s. Since then, it is understood that that form of a pressure here is producing features that are unrealistic, that are blatantly unrealistic. One doesn't even need to look at data. So the traffic flow community has since then agreed that there are other ways to prescribe the pressure here, for example, like in the so-called All-Russell-Jang model, that remedy these problems. But the analysis that I'm presenting here works equally for these other types of descriptions. So I'm just, for historic reasons, sticking to the Payne-Witham model here, but please bear in mind this works equally well for these other models as well. So the structure that you get here, the traffic pressure, can be interpreted as if you just relax on a continuum level, if you just relax, eventually you will get solutions that don't make sense, vehicles piling on top of each other and things. And the pressure here, practically speaking, models some form of preventive driving. That's one way to rationalize it. Mathematically, you can say it's needed to render the model well posed. Either way, that is a typical structure. Now, there are second-order models that have 0 in the right-hand side, so they don't have a relaxation term. And I want to point you to part 1 of the lecture by Dan Work, where yesterday he actually presented an example of such models. And these second-order models then would not capture instabilities, dynamic instabilities and phantom traffic jam phenomena, but they still have the capability of capturing a spread in a fundamental diagram. But there's 2 differences. Let me go back 1 slide here. Second order models with a 0 in the right-hand side, so that are stable, that are dynamically stable, can capture the spread by one fitting not just one single curve, but fitting a family of curves in here. That is what in other papers is called generic second order models. But these don't develop dynamic instabilities. What I'm going to talk about here is something that reproduces this spread dynamically by principled approaches. So both of these ideas and concepts are possible. Of course, they result in very different dynamics that one sees as one runs these models forward in time. So let me focus on that second part. If you're interested in that first direction, so you don't want instability, so you just want to capture the spread, I want to direct you to part 1 of Dan Work's lectures that are also recorded. So if you want to understand these models, this is quite interesting. And these kind of model structure arises not just in traffic flow, it actually very similarly arises, for example, in detonation waves or in equations describing roll waves in open channels, for example. So these traffic waves are actually integrally related through these equations here. So you have a hyperbolic part, and then you have a relaxation term here. And now you understand how the solutions of these problems behave. So you can formally just consider the limit tau going to 0, right? So intuitively, that would make this relaxation term more and more dominant. And Stan raises his hand.
Can you hear me?
Yes, I can hear you.
Very quickly, your 2x2 system is not in conservation form. You have conservation of velocity rather than
yes. Yes.
momentum. That doesn't bother you, I guess.
It doesn't bother me because I know how to do it right. Yes. So thank you very much, Stan. Yes. So one thing that I want to point out is that these are not written in conservation form. So while the density rho is a conserved quantity, in these models, U itself, the field U itself is not a conserved quantity. Even if I set this term here to 0, this structure here does not conserve the quantity U. In fact, if this pressure is written here, what is conserved is the quantity rho times U. That would be the field that is conserved. One could give that a different name, Q, for example, and then write this as a conservation law in the variables rho and Q. So strictly speaking, mathematically speaking, what I'm writing here is a notation that stands in place for the conservative form of these equations. Stan, the reason why I'm writing this is because I find it much more intuitive to write it in this UT plus UUX form. But what has to be stressed, whenever one does analysis, in particular the shock conditions, and one does numerical methods, of course one has to cast this problem in the row T form, in the row Q form, and implement it this way and analyze it this way. Again, while the solutions are smooth, both of these forms are completely equivalent. But if one talks about shocks, then one has to carefully deal with shock jump conditions that consider the conservative variables. One could also, of course, that's less common, but one could even cast this model in these non-conservative variables and just say the shock conditions, the jump conditions that hold are the ones that come from the conservative form. So that is the right way to understand these models. Does that address your comment?
Yeah. Okay. Makes me nervous, but
no need to be nervous, but yes, thank you very much. That's important to point out, right? So I'm staying a little bit on the intuitive level, but if you want to use these models and see how to implement them, by all means, don't use only this talk as a basis. Please look at our corresponding papers or papers by other people that tell you how to actually properly analyze and implement these models.
Great. Okay, thank you.
Yep. Okay, good. So yeah, this is very important. So either way, intuitively, we're writing in the U variables because those are variables that were really like that are intuitive, right? Because this is the vehicle acceleration here. So if you want to understand how the solutions to these models behave, one can intuitively think of what happens if I make this relaxation term more and more strong. Then, of course, you could say, well, if that dominates, then the little u gets closer and closer to the capital U, and the limit of little u being equal to capital U, you can just substitute it in the top equation here and recover actually the LWR model. So the LWR model, the first order equation, is actually a reduced equation of the second order dynamics. So now one could think, okay, well, what if I let tau constant, but let t go to infinity? Well, would that still in time relax towards the first order model? So is the first order model a limit of the second order model? And the answer is, as oftentimes in science, it depends. It depends on a specific condition that is called the subcharacteristic condition, and that is as follows. This 2x2 system has two characteristic speeds of information propagation. Here, one speed is u plus c, one speed is u minus c. Again, that these are the eigenvalues is due to the Payne-Witham structure of the pressure. In other models, like the ARZ model, you would have not u plus c, but just u here, which is more realistic, but it doesn't change anything about the structure. You have two eigenvalues. Those are the two speeds of information propagation that this model is able to produce in space. Then you have the reduced model, in this case the LWR model, and that is one characteristic speed, the speed of information propagation that we saw yesterday. And the subcharacteristic condition is said to be satisfied if the speed of information propagation of the reduced model is in between the two speeds of the second order model. And already Witham showed in the 50s that that subcharacteristic condition satisfied is actually equivalent, modulo details when you have equality here, is equivalent to the second order model converging in some sense to the first order reduced equation, and also equivalent to the second order model having a base state at this corresponding density value at which you evaluate these eigenvalues, that base state being linearly stable, meaning you take a base state that's constant, all cars being equispaced, moving at the same speed, perturb it a little bit, and then these perturbations will grow exactly if the subcharacteristic condition is violated. Otherwise, they will remain bounded or even decay. So if you plug in some reasonable, simple, but somewhat reasonable functions for that pressure and the velocity function here, then you will get that there is a phase transition in these models. There's a critical threshold density. I call it rho c here. That's bad notation because that's not the threshold density. It's a different density that depends on the driving behavior. If you're below that density, uniform flow is stable. And if you're above that density, uniform flow is unstable. So these models reproduce, can capture this phase transition behavior that agrees with what is observed on real roads. Moreover, one nice thing about these continuity descriptions is that you can really easily define traveling wave solutions because you have object densities defined everywhere. You don't just have quantities defined on the vehicles. So you can make a traveling wave ansatz that both density and speed here are functions of a single variable that is just in a moving frame of reference here. And you substitute that into the two equations. You get a relationship between rho and u with some unknown traveling wave speed s, some integration constant m that turns out to be the mass flux of vehicles. You substitute that in the momentum equation and reduce the two-vector system of PDEs to a single ODE. That is called the Jammeton ODE, and that is a procedure and an equation that resembles extremely closely what is actually known in detonation theory, called ZND, Zeldovich von Neumann-Düring theory. And many of these techniques that are well known in that community can actually be borrowed to understand these traveling wave solutions. And there's a lot of more interesting things, really interesting structure that can be studied here. I'm going to leave it like this here because I want to give you a glimpse. There's more in the literature that can be found about this, but the main point is that these dynamic instabilities in traveling waves can actually be captured by second-order models, macroscopic second-order models, and we can even very nicely understand these traveling wave solutions. This is, again, the video of the seminal Sugiyama experiment that every talk on traffic waves, of course, needs to display. So again, researchers put a ring road of cars. They place them equispaced. Initially, they roughly drive at a uniform speed. Of course, there's always little imperfections happen, but the question is, do these perturbations amplify and systematically grow and drive the system away from a uniform flow, or is the uniform flow stable? And you see in this case, the uniform flow turned out to be unstable. The system was driven away from it and dynamically went actually into a state that is a traveling wave solution that goes backwards along the road. That appears to be an attractor of the system, and certainly dynamically stable because it persists, right? It travels backwards. And now, see that ring road as a proxy for an infinite road, right, with many vehicles. Of course, some periodicity here, but if you see it that way, that could then resemble that this phenomenon that you sometimes see these waves of brake life, that you brake, you look around, you accelerate again and see no apparent reason. Well, this is an explanation, dynamic instability, of course, that this can happen from the collective driving behavior. Now, this is, I think I showed this in the first talk as well, but just to show this again, this is a mathematical idealization, right? So a calibrated model on these macroscopic parameters that reproduces the observed behavior qualitatively, in fact, quantitatively, even on the shock speed level. So it's a purely macroscopic description where density function is defined everywhere, but just for visualization purposes, you see the cars out here, and it's periodic, so what goes out on the right comes back in on the left, and you see that a small perturbation of an initial uniform flow grew in some complicated transient way, but then you got some traveling wave solution in the end here out of it. So, and that model, of course, the cool thing is once you take a model and you calibrate it in a specific setup here, the 230-meter ring road here, then you can, of course, take the same model and run it on different scenarios. That's the beauty of having a principled model. So here we take now a long road with an inflow and an outflow condition that is 6 kilometers long. We start with a uniform flow state that is unstable, but we add a small perturbation only at one point. That perturbation grows into this lead wave. And these traveling waves, because they're nonlinear traveling waves, we call jammetons, as a play on the word soliton, which is a nonlinear traveling wave in physics. And you see that here, the initial lead jammeton that arises locates more cars in it by conservation of mass. That produces a dip downstream that grew in another instability. That produces another dip, grow in another instability. So you dynamically get this whole train of stop-and-go waves, or the lead jammeton gives birth to a whole train of jammetinos that follow behind. So if these models now have something in reality, that would predict that if you had an effect that you had a phantom traffic jam, you had to brake unexpectedly and then accelerate again, it's likely that this will happen again downstream of the road 30 seconds later or a minute later. And again, that oftentimes agrees with what one observes in reality. This tells us a lot. For example, it tells us that to get these stop-and-go waves, you don't need to have bad drivers on the road. It's not that you need one person at fault who was braking too much and then triggered this wave. It can actually rise if all drivers are behaving exactly the same, behaving completely deterministically. They can arise just by dynamic instability and some small perturbations that happen to the system. That doesn't mean that there are no bad drivers on the road, but it means that these phenomena can arise without these, and can be explained without these phenomena. So it's really, this is what models, what's really fun about these models, right? Once you have a principled model, you can then run it and simulate it and study it and see what it predicts and then compare what it produces as phenomena. There's a lot of interesting mathematical questions, but I want to stop it here on these dynamic stuff. I just want to finish with the point, of course, about the fundamental diagram. So if one now looks at all possible Jammerton solutions that can arise, they actually form a set here. So around every of these red dots, these are the states that are unstable. The black dots here, these are states that are stable. So what you will observe is more or less being on that curve. But once you start out with a uniform flow here around one of these red dots, it actually develops in these traveling wave solutions, and they lie on one of these line segments. So that would be if you could measure things instantaneously, point-wise, the density. Of course, we discussed yesterday, it's impossible to define a density based on a single vehicle. You always need to consider a window that contains multiple vehicles and recover macroscopic variables from this, either just by counting or by doing a kernel density estimation techniques. If you emulate detector data on top of the model, so we run the model and we emulate aggregated data over at stationary sensors over 30 seconds, then some of these high data points are not observed because they averaged out against low data points. And then you, for example, can reverse engineer the model parameters to fit qualitatively with a fundamental diagram, and one can even fiddle around to reproduce the spread of the fundamental diagram. To be clear, in reality, the spread of the fundamental diagram is not solely caused by waves. So we're exaggerating things here. In reality, there are other effects that play a role, but they do also play a role for the spread. And the point is that one can attribute the spread or parts of the spread in a systematic fashion to these waves and these models. And it can be done on a continuum level. So again, these models don't resolve every single vehicle, so they're easier to scale to whole urban city scales, for example, and can reflect privacy, are more robust to small perturbations, little noise, and so on. So there's a lot of use cases of these macroscopic models, and these phenomena can also be captured. Now let me move forward to cellular traffic models. And let me make a distinction here. One is that there are cellular models that are derived or can be derived from macroscopic models. And then there's intrinsically cellular automata models. And I'll do one slide on those as well. But let me first start with what people call more like the cell transmission model. So the cell transmission model in the traditional literature is written down as a cellular model. It doesn't talk about partial differential equations, but an important fact is that the classical cell transmission model and most other examples are actually numerical discretizations. They're equivalent to numerical discretizations of continuum models. Specifically, the classical cell transmission model is actually equivalent to the Godunov method applied to the LWR model. So again, the first talk by Dan Work mentioned some of these aspects as well, so I would like to direct you to this, but I want to highlight the method in a few minutes again here, because I think it's very insightful to recognize this and know it. And of course, it also can guide if one wants to modify a discrete cell transmission model, that there's a whole body of literature, of course, on different numerical methods that could be employed. So here's our LWR model. I now call the flux function F here. Again, mathematical notation, but that's the same flow rate fundamental diagram curve that we have. So we have a given model. And then the idea is as follows. You take a given initial condition, you chop your domain up into different cells of a mesh size H here. And then I replace actually this smooth function by just averaging it over each cell. I replace it by a piecewise constant function. So in every cell, I let the function only be constant. Then if I have 100 cells, I have 100 degrees of freedom that represent the state of my system. And now I actually evolve that solution exactly, analytically. At least for the moment, to think about it. So why? Because locally here, this all looks like a Riemann problem, and I know how to solve a Riemann problem. As we discussed yesterday, for the concave down flux functions here, it's either a shock or it's a rarefaction wave. And for both of these, I can actually construct it here by method of characteristics, here by the Rankine-Cournot conditions. So specifically, if it jumps up the density, you get a shock. Shock can move to the right, because here in your free flow, shock can move to the left, because here the congestion regime overwhelms the free flow values. So the slope of the secant line is negative, right? Here it jumps down, so you get a rarefaction by the entropy condition, rarefaction by the entropy condition. You could get a stationary shock also that just sits there. But either way, you can solve this exactly. You solve it up to a time that is small enough that these local Riemann problems don't interact with each other. So that is a time step restriction that is given by your spatial resolution and by your maximum propagation speed that you can have. And then you evolve it a little bit into the future. And then, of course, the status on each cell has changed a little bit. And then you average again. And then you're done to this first step here and can keep on going forward. And that marches your numerical method forward in time. You see that this step here is exact, but then the averaging step, of course, that's an approximation. So ultimately, qualitatively, what you get will only be an approximation to the true solution of the LWR model. And in fact, it's approximative in the sense of that it smears the solutions. So in practice, this averaging step will then give you not sharp shocks that you see in the whole profile, but they're smeared over 10 or 20 cells. But oftentimes, that's a price that one is willing to pay, in particular because real shocks are not there anyways, right? And zones are smeared anyways. Of course, that you shouldn't rely on your numerical method to reproduce the smearing, but just from a practical perspective, in applications and engineering, people don't worry about that fact that this is only a first-order method, and it works very fine in applications, particularly because one can calibrate the model parameters to the discrete CTM rather than calibrate it to the continuum level, and it turns out to work rather well in practice. So for anybody who's interested in high-order methods, these so far have not found much of an application. In these fields, the first-order models serve the purposes and the needs quite well. So now, of course, you don't want to implement a method where you want to implement the exact solution. And it turns out, of course, you don't need to, because all that matters for the change of the state that happened from one to the next step is actually how much flux went through the two cell boundaries. So if I want to know how much did the state get lowered here, I just need to know how much mass was flowing, how many cars were moving through that boundary, and how many cars were moving through that boundary. And my total update rule, the density at the cell j at time t plus delta t, is just changing by whatever, well, delta t over h times whatever the balance of the fluxes is, right? Influx minus outflux. And you see that resembles exactly how we derived the LWR model yesterday as being a conservation law. So all you need to understand is what are these fluxes, and these fluxes here then depend on what your local Riemann problem is. Specifically, let me go back here. If it is a left-going shock, you see that this state here remains constant of the right state, and the flux is the flux function evaluated at this right state. If you have a right-going shock, locally here it's the left state, and the flux that you get is constant in time over that time step, just the flux function evaluated at the left state. And if you have here a rarefaction that goes through the critical density, where the flow rate is maximal, then this will be the flux, right? The maximal flux. So essentially and otherwise, if you have a right-going rarefaction here, then it's only the left state again, right? So it's either the left state or the right state, or it's the maximal flux, right? So these are the three possibilities, and I can exactly characterize what happens in what situation. So that can be worked out, and then one has the Godunov method, and that's all one needs to do. Now, the CTM, as it's written in the literature, is oftentimes it's equivalent, but it's written and interpreted in different ways. Specifically, this is usually written in a following way. One defines a demand function or a supply function. These can also be called a receiving function and a sending function. So to be clear, this is not a supply of vehicles. This is a supply of road capacity that corresponds to the downstream cell into which the cars want to go. And this is a demand on road capacity that depends on the state of the cars in the sending cell, in the upstream cell. And these functions are defined as follows. You take the flux function, that is, for example, this parabola here, and the demand function is one that follows that parabola up to the maximum, then remains constant. Because if I'm congested in the receiving cell, I will still have maximal demand. It will not go down again. And this supply function here is doing the opposite, right? So it's in the congestion regime. If you're congested, you have less and less supply. But if you're free flow, you still have the maximum supply of road capacity. It doesn't diminish by having even fewer cars. So you just stay maximal here. These are the supply and demand functions, how they define. And then the actual flux is just the minimum of these two. And the principle behind is that the minimum of the demand and supply is as follows. The flux that actually is realized, it has to be less or equal than the demand, because you cannot send more vehicles through the boundary than there are, right? And it has to be less or equal than the supply, because you cannot send more vehicles than the receiving cell can take. And therefore, and the principle that is then employed here that makes it equivalent to the Godunov method is that among all such feasible flows that are less or equal than the demand and supply, you take the flow that is maximal. And that will be exactly given by this formula here. And that is the principle, and one can easily check that this is completely equivalent to the Godunov method, but is a neat way to interpret it and to write it down and to implement it, because you imply every boundary property of a function, demand function on the receiving cell, on the downstream cell, and supply function on the upstream cell, and then you can implement this formula here. And what's also neat is that if you have a network coupling condition, so like a road goes in and then you have two out roads, for example, the same kind of framework can be employed. One has to deal something with split ratios and define these things, but in fact, it can also be employed in a very, very similar fashion, which is quite intriguing. And also, when you look at second-order models, like we discussed before, these principles can also, to certain second-order traffic models, be generalized. And again, I want to point you to Dan Work's talk that was given yesterday. All right, so that was on what people call the cell transmission model in practice. There are also people call cellular models that are intrinsically cellular automata models that are not derived from a continuum equation. And one example, for example, is the Nagel-Schreckenberg model. I invite you to the Wikipedia page, which I think is quite interesting to see. So here's a simulation just taken from Wikipedia. So again, it's a stochastic model that chops up the road into cells, and then each cell either has a car in it or not. And then you have certain rules of how a car can move forward. So one travels 1 or 2 or 4 or 6 cells downstream. And then you have update rules, how we do that cell by cell. And when you do it, and you have some randomization here with some probabilities, so you have to usually run it multiple times to get an ensemble, but generally it produces effect like this. So the cars move forward along the road, but then you get certain clusters and waves that move backwards along the road. So stop and go traffic waves in a sense. These models are fundamentally different in terms of the analysis and so on, and how they're set up than the models that we saw before. One thing that is intriguing about them is they're very easy to implement and very fast to parallelize. So one can simulate very quickly things with this. And also, if one does proper analysis, one can show that in certain limits of cell size going to 0, these models do converge to certain PDs. I want to point you to this website here. If somebody actually could just type this into the chat window. So this is just going to my website and then clicking on teaching, and then the course from 2018, 2100. Somebody could quickly do that, that would be great. And then there's several MATLAB codes, and one is actually just an implementation of this model. So if you have MATLAB available, the software, you can just run this, and you will see a simulation of this model that can be quite easy and illustrative to do on the side. So I invite you to do that. All right, that is it on cellular models. And now let me move into microscopic models. So the last topic that I'm covering here. So microscopic models now are, in a sense, the most natural way, because you just capture the vehicle itself, right? So you describe a dynamic law for each single vehicle on the road, and you simulate it. So you compute the trajectories of every vehicle. And obviously, you can do all kinds of stuff because it's relatively intuitive. Of course, you need to know a little bit about dynamical systems. You need to know a little bit how to approximate them numerically. There's quite some coding effort required to make this all work. But in principle, you can extend it to multiple lanes. With the lane switching model, you could easily change vehicle types, have heterogeneous traffic flow, and lots of different things. In principle, these microscopic traffic models, so dynamical systems, ODE models, are at the core of most microsimulators. For example, the Gibbs model in NameSum, the Wiedemann model in BizSim, the Krauss model in Sumo. Many of these allow different models as well, but just to highlight that there's many models out there. But some people say too many models out there. And then they're implemented. Of course, there are always discrete approximations of these models with a discrete time step. And then oftentimes one doesn't want to choose tiny time steps, or high order methods, again, are difficult to use because the number of cars on the road changes constantly and so on. So oftentimes these are time stepped and then calibrated to the time discrete systems, and then also fail safes. Like if my numerical integrator produces a negative velocity, I just make all the velocities 0, and lots of stuff. If cars bump into each other, I just teleport them a little bit. There's a lot of fail safes that are called in these things that are quite a plague sometimes because it's very hard to rationalize what's at the core of it on these models. But there is sometimes a necessity to just do it if one wants to get something that's competitive and fast and practically applicable. So there's a lot of compromises that have to be taken with these microsimulators because some of these really are used widely by stakeholders and companies and so on to conduct scenario simulations, and they need to be workable. There are lots of other car following models. For example, one that's very popular is called the intelligent driver model. So again, I invite everybody to go to Wikipedia and other resources and just read up on this. Many of the Wikipedia articles are quite good on these models. These models may have many parameters, and many parameters that don't have an immediate physical interpretation, that just there's a parameter in front of this term. And so calibration is important, right? These need to be calibrated to what is observed. And of course, if one is asking for more and more complicated things, so not just match the average flux at a given point, but more complicated features like the correct braking profiles and so on, the calibration task itself is non-trivial and quite an art to be done. Which is also why some of these are actually commercial packages, because it's not so easy to do these things. But it can be done. There's a lot of experience out there on these models, and there's a lot of existing simulators. To be clear, Einstein and Vissim cost money. Sumo is an open source, freely available example of a microsimulator. It's natural and common in these to add randomness. Of course, if one adds randomness, one has to be careful to not just do it completely ad hoc, but have some rationale for this. But obviously, there's some intrinsic irreproducibility among driving. If I expose the same driver to the same situations, they might have some different mood on that day, some different hidden variables, and actually drive slightly differently. And of course, that can never be measured. So a simple way to model this, even though it could be criticized, but the simple way is to just add a little bit of random noise in every step, right? And say, okay, that produces an irreproducibility, and it does the job. And then, of course, one needs to interpret the results by running suitable ensemble simulations and asking for suitably averaged quantities. So again, there's an art on how to use these microsimulations properly, but if done, they can be extremely powerful. And they're very popular for offline simulation. For example, you represent a correct physical model that's reasonably calibrated to a segment of highway, and then the Federal Highway Administration might ask you, what happens if lane closure happened here to a construction site for a month? How will that affect, for example, the air quality? That's actually a federal law, at least last time I checked, it still was, that every study has to be done about the air quality, and many of these microsimulators are used for these tools. Right, so long story short, these play an important role also in practice, and of course also for studying autonomous vehicles. They provide an intriguing framework, but one also has to highlight, of course, some of the difficulties and challenges and disadvantages. So it is, in my view, critical to know about many other descriptions of traffic flow as well. So in a nutshell, a simple framework is car following. Car following means essentially that what my car does here only depends, my car XJ only depends on what the car immediately ahead of me is doing. That is a good approximation in many cases to how humans drive, even though, of course, in reality, if you can see two cars ahead, you will, of course, not say, oh, I completely avoid what the car two ahead is doing. But it turns out that, again, all models are wrong, right? So that you take a model that only depends on what the car ahead does doesn't invalidate the model per se if you can carefully calibrate it. Yeah, so that is a framework that is quite successful, and it's reasonable for human drivers. Again, you have the vehicle length here, you have distance xj plus 1 minus xj is the spacing, and then if you subtract the vehicle length, then you have the gap. The gap sj, I do a vehicle ordering like forward along the road, but that of course then means that vehicle j is following vehicle j plus 1. Okay, so plus 1 is the lead vehicle of vehicle j. And then, for example, I could put them either on a ring road, right, going around like this, or an infinite road with one vehicle leading. But of course, if I want to simulate this, I only can simulate finitely many vehicles. But so ring roads are quite a neat way to do it, but you could also do an inflow and an outflow, for example. So there are different kinds how they can be arranged spatially. And then one could, for example, do a first order model, x dot of j, so the velocity of the jth vehicle is just some function of the gap to the vehicle ahead. Or I could even say of the gap, add time tau into the past. Okay, so put in the delay, for example, could do that as well. I could do a second order model where I prescribe the acceleration. Obviously, a car weighs 1.5 tons. It it would seem more natural that one would prescribe the acceleration, right? The force that acts on it rather than prescribing the speed. But again, that doesn't make it a bad model here. It just depends, right? It depends on the situation. But of course, these are just Newtonian laws then, Newton's laws of motion, and this is the force that acts. And now you say that is some function of the gap, the rate of change of the gap, which is the velocity difference, and the speed of the vehicle itself. One could also add a delay, but usually that's not necessary because the second order dynamics capture the phenomena that are needed. Now, a natural starting point that should always be done for understanding a given model is study its equilibrium behavior. So take a uniform flow, and assuming that that, of course, is a feasible solution, and then fact that the model admits exactly those solutions as equilibrium solutions. So all vehicles drive equispaced with a constant speed, and then you can take this equilibrium state, where cars just move in straight lines in the xt diagram, and linearize it around that state where yj is the perturbation. You take this ansatz, substitute in the equation, take only the terms, remove the terms that are infinitesimally small, which you get by Taylor expansion, and then you get a first order linear equation. For example, here's v prime in the first order model evaluated at the equilibrium spacing, and then it's just a linear model, a cascade model that goes backwards. Or the second order model, same thing. You get a linear model here that in a second order here, it's first order terms here, and then the difference here in the perturbations, and you have coefficients that are partial derivatives of the function f with regards to its three arguments evaluated at that equilibrium state. And now, if you want to study these linear models, you can now do a stability analysis. There are multiple ways to do a stability analysis. You could write it as a big matrix and look at the eigenvalues, or what is neat, of course, always when you have this here, look at things in frequency space. So, for example, you can make a Laplace Transform ansatz saying that the perturbation is just some function e to the omega t, where the real part of omega would mean that it's a temporal growth or decay of the perturbation. The imaginary part is the oscillation frequency, and then some unknown amplitudes, Cj. You substitute that into that law that you get, and that law then gives you essentially an input-output system. Given the trajectory that here on the lead vehicle here, it induces a corresponding trajectory on the follow vehicle. And how the follow vehicle's oscillation trajectory behaves relative to the lead vehicles, that is given now by the so-called transfer function. So in engineering, especially electrical engineering, this is completely common, and one can calculate the transfer functions of these two different model descriptions. They're written here for the first order model with delay, here for the second order model, and then one could look at the magnitude, the modulus, the absolute value of the transfer function. That will be the growth and the decay across vehicles. So that value here will tell you for a given frequency omega, if the lead vehicle has an oscillatory perturbation of a given amplitude, then this will tell me by how much this amplitude is amplified to the vehicle behind. And this here is then a phase shift. Now, plotting this for all possible frequencies omega that are not growing or decaying, but are just oscillatory profiles, that in engineering is called the Bode plot. And in fact, doing that here and plotting the absolute value of f for all omega that are purely imaginary then reveals to you whether there are some modes that are unstable or not. And if this here is less or equal than 1 for all possible omegas that are purely oscillatory, so among the imaginary line, then your model is actually stable in the sense of string stability, meaning that one vehicle might oscillate, but the vehicle behind will not oscillate more. And if there's some omegas for which this is larger than 1, then it would mean one vehicle oscillates a little bit, the next one oscillates more, the next one oscillates more, and then of course this cascades, right, and grows out of bounds, and that would be the key mechanism for instability. So that is what people call string stability. There are other notions of stability that also have to be studied and looked at, but this is the key notion that matters. And of course, one can work it out. It's somewhat technical, but one can work out that this reduces to algebraic conditions on those coefficients here that you get from the nonlinear function, linearized and evaluated at equilibrium. So again, there's this in the literature, but this is neat, and it's a critical ingredient to be done. In fact, if one stays on that level of only studying small perturbations of a uniform flow, one can do a lot of more things that are interesting. And of course, the practical idea is that if I just know that a uniform flow is unstable, I know it will grow. I don't know what it grows into because at some point nonlinearities will kick in. what is observed is for most reasonable models is that you get traveling wave solutions that are very close to what we saw before. But of course, for other models, you could just have that the vehicles crash into each other, right, and collide. It depends, right? And that depends not just on the uniform behavior, but then depends on the nonlinearities in the model. So these models, of course, have more requirements to be designed. But one important aspect is that these instabilities are not something undesirable. Oftentimes, they're a design feature because you know that traffic flow in certain regimes develops instabilities, and you can calibrate your parameters accordingly to capture some of these effects. And then, of course, one thing that's really nice about microscopic models is it's completely natural to put in different classes of vehicles, heterogeneities. For example, to draw some connection to autonomous vehicles, you could take a human driver model that is characterized by the parameters alpha 1, alpha 2, alpha 3 around a certain equilibrium state, and make it for that equilibrium state actually slightly unstable. Modeling the real driving behavior has an instability, and then put in other types of vehicles, for example, autonomous vehicles that have a different car following law. Ideally, not too different from the humans, because if you put in cars that drive completely differently from humans, that will probably not be perceived as being too reliable by the humans. But of course, practically speaking, autonomous vehicles have to be programmed to behave differently from humans because humans sometimes do stuff that's not good. And that, of course, must not be reproduced by people who program autonomous vehicles. So this G will be slightly different, and this is a completely abstract setting here, but I want to highlight a little bit how these microscopic models and just the linear analysis can already reveal a lot of interesting structure about this. For example, what if I have a few autonomous vehicles in there, and let's assume that this G is so that if the autonomous vehicles alone would actually be always stable, right? Could then sprinkling a few autonomous vehicles into the flow, or could be human drivers that just drive in a stable fashion always, could that stabilize the whole heterogeneous system, the whole traffic flow? Okay, and that's, for example, a very good example of a very interesting question that can be answered, studied here, almost analytically. And there's a lot of interesting aspects. So for here we would have a transfer function f for the humans, slightly unstable here, transfer function for the other cars, like control vehicles or autonomous vehicles, and you can ask, can a few autonomous vehicles stabilize the traffic flow? Well, the stability condition is that if the penetration rate of the autonomous vehicles is gamma, it's just this G modulus to the power gamma times the remaining power of F, and if that is less or equal than 1 for all possible oscillation frequencies, then you have stability of the whole system. And in fact, if one works specific numbers and values here, one can actually find, theoretically, that any number of vehicles that you take, and then just a single autonomous vehicle can stabilize the whole traffic flow, for example, on a ring road, which of course is completely unrealistic if you think about it, because if you have 1,000 vehicles between you and the control vehicles, why would that be able to stabilize traffic near you? So there's some weaknesses, right, in the modeling, and actually an interesting aspect is can one explain this, right? One thing that turns out is that these models actually are quite intriguing structure. Mathematically speaking, they're highly non-normal systems. So you can formally get a system that is actually asymptotically stable, so that as t goes to infinity, as any perturbation will eventually decay. But if I give a single kick here, this is time here, and this is the vehicle index, and I have a single control vehicle, and then the vehicle that's just behind the autonomous vehicle, I give it a little perturbation, and that perturbation now grows and grows and grows and grows until, of course, it hits the autonomous vehicle. This wraps around here. That dampens the perturbation substantially. It dampens it by more than the collective human driving behavior had amplified the wave, and this dampening of the AV being stronger than the collective amplification makes the system asymptotically stable as t goes to infinity. But there is a transient time by which the size, the magnitude of the perturbation has amplified by a lot. And it amplifies exponentially by the number of human cars that are in between autonomous vehicles. So therefore, asymptotically speaking, and if you have infinitesimal perturbation, that is still perfectly fine. But for all practical purposes, if your perturbation is just small, of course, this could be amplified by a factor of 1,000. before you get the next control vehicle. And practically speaking, then the system is not stabilizable. And one can even rationalize this by adding a little bit of noise to the system and show that the expected deviation, in fact, grows exponentially with how far you are from a control vehicle. So what is neat about this is that it highlights a lot of really interesting structure already about heterogeneous traffic flow in the near future, where we'll have most cars still be traditional human controlled, but maybe a few cars that have some level of automation, or even the current situation, and understanding the consequences of behavior on these systems is quite neat. Now, this is nothing nonlinear here. The nonlinear waves, once you let it go, of course, develop more interesting situations. But of course, the point is, if you have a stable system and you don't explicitly push it out of its system, it will remain uniform. Boring from a sort of dynamical system perspective, but desirable from a practical perspective, of course, right? And this can be seen in these models. So this sort of as a showcase on what this can do. And I see that now Sharon has raised her hand.
Oh, thank you. Hi, Ben. So you mentioned that so AV have a function, say G, but can you describe a little more how you design that G so that AV can drive more stable than human?
Yes, so that is exactly, when you do the simple analysis, it looks so pretty, right, and beautiful. So there's a lot of practical challenges. So first of all, I'm assuming that I linearize the system around a given equilibrium state. So first of all, what this assumes is that vehicles are programmed in a way that they leave exactly the same equilibrium spacing as the humans do. Of course, the problem with humans is that in reality, they don't actually all leave exactly the same spacing when they follow, but all cars go with the same speed. Some people tend to tailgate a little more. Some people tend to have a bigger spacing. On average, of course, there is an average spacing still that arises in the system when they all move at the uniform speed. But that could even be regionally dependent, right? So in practice, the AV would actually need to infer what this equilibrium state is, because in practice, it is actually not given to the vehicle and is not known. And that is a fundamental assumption, of course, that is made here, that A, the vehicle can infer what the equilibrium state of the traffic flow is. And while this is challenging but doable while all cars are moving at the same speed, if you come in and you have already oscillatory traffic flow and you want to dampen it, this is highly non-trivial to infer what would be the correct equilibrium state. The relationship between speed and spacing that I would need to prescribe if the traffic flow were stable. So practically, there's a lot of complications on how to do that estimation problem. Once you have addressed that estimation problem and you drive at the same equilibrium spacing as humans would, by the way, some people argue that AVs, of course, can drive reliably at a much shorter spacing. But I would argue that that should not be done if an AV is following a human, because people have rear mirrors and look behind. That platooning effect of driving at a much shorter distance is feasible if you have a platoon of multiple AVs. Then you could, in principle, do that. But I would not advise to even consider implementing this following a human driver, because I would be completely freaked out and do things to get away from this AV. And that, of course, would add extra instabilities and perturbations. So you don't want to do that. So and if the vehicles are really sparse, the platooning idea is unless you have really long trips or trucks, right? But for passenger vehicles, I see less of a role of that if you talk about penetration rates of 1% or something, for example. So anyways, these vehicles should still drive close to the equilibrium state to what the humans do, and then they can be linearized around the same equilibrium state. Then you need to choose, of course, the gains here, the control gains of how they react in their second order dynamics to different things. And of course, again, you want something that is somewhat reasonable to what humans have. So this needs to be learned somehow from the humans have. But once you have done this and you have the model structure, so let's say you implement a controller that acts on the level of the acceleration, then you can use some theory, right? Stability theory like this one here, or more general notions of stability theory to understand, okay, well, how should I choose my control gains in my controller in a way that I, for example, would optimize stability under some constraints of being still reasonable, for example. And then this theory, these frameworks can actually be applied. But your question is right on, Sharon, right? I mean, this all looks so simple, but in practice, there's a lot of fundamental challenges to actually making this work. Does that answer your question?
Yeah, so but in your next slides, so basically you assume you already have determined G or this G omega thing, right?
Yes, so I'm assuming that somebody gives me a control law on the cars that preserves the same equilibrium state as what the humans would do, and then has the correct control law, and the control law is of that same car following form. So the car, and of course, real highways have also lane changing and so on, right? This is an idealization of a single lane, right? Just cars on like beads on a string moving forward. So here I assume that it's just a law of that same form. So sorry, here nonlinear function, right? The acceleration that the car is implementing is some nonlinear function of the gap to the vehicle ahead, the velocity difference, and my own velocity. That's what I'm assuming, and I'm assuming that that function g then for the autonomous vehicles for that equilibrium state that I care about has the same relationship between spacing and speed that you would get by evaluating that function. When is the function 0? When you set the middle term also equal to 0, right? So those are the assumptions here in this study is if somebody gives me that function g, can I make the system, can the system be stable? Under what circumstances is the system stable? And what happens if I have sparse controllers? What are interesting consequences, the structural consequences that arise? If you want to do the inverse problem, that's of course always harder, right? Like how can I design the function g, given that I have a certain penetration rate of vehicles and I want to make the state as stable as possible, how can I design the g? That, of course, is a problem that I haven't addressed here at all. I'm just providing a framework that one can cast it into that can guide what one can do. Then again, one could say if your goal on the control is to just dampen stop-and-go traffic waves, then in principle, the best you can do is very easy. Just drive at a constant speed, right? And how to choose that constant speed? Well, choose it exactly so that when the cars ahead of you are doing stop-and-go traffic, that when they accelerate, you don't follow that acceleration. You just go at constant speed. And then when they brake again, you hit the wave exactly at the moment that you smoothly go into the cars again without having to brake ever, but without falling behind either, right? So ultimately, you could also argue, well, these controllers are on the core of things are very simple. Just have the cars drive the constant speed and estimate that speed as well as you can based on maybe some non-local information. In fact, in a few slides, I'll show a simulation that does exactly this. So maybe we can also move forward. I see that Ronan Keane has raised his hand.
Hi, yeah. So I was wondering if you could talk about the relationship between the stability analysis for the linear system and the nonlinear system. So if I understand it correctly, I think if the linear system is stable, then the nonlinear system will also be stable, right? But isn't it possible that the linear system can be unstable, but then the nonlinear system will still actually be stable?
Mm-hmm. So one thing that has to be stressed here is that systems are not stable, solutions are stable, right? So one always has to talk about the stability of solutions of a problem. So here in this case, your question, I presume, is still focused on the stability of uniform flow solutions, constant speed and equispaced cars solutions.
Oh, right, yeah.
Yeah, because one could also ask about stability of nonlinear traveling waves, for example. But yes, so if you're concerned with stability of uniform flow solutions, then what I'm doing here is just the basic linear stability analysis that essentially assumes that the perturbations are infinitesimally small. If you talk about perturbations that are small, but large enough that the terms that are thrown away when one conducts the Taylor expansion here actually matter a little bit, which in a special case is if you have some neutrally stable modes in the linear stability analysis, that would be the prime example where this matters here. Then, of course, there's more complicated statements. In particular, of course, even if all the modes that matter in the linear stability analysis are asymptotically stable, so they came to 0. By the way, there's one mode that's always neutrally stable that's due to the shift invariance, but that one is trivial. It's just shift the system. So that one you can neglect. So it's possible that all other modes are asymptotically stable. Then, of course, it could still be that if your perturbations that in reality happen to the system are of a sufficiently large size, which is actually realistic in traffic flow, that they still push you out of that infinitesimal regime, and the next order terms matter, for example. So there are more sophisticated tools of analysis, and it is in principle possible that if your perturbations that act on the system are sufficiently large, that your system, even though it's linearly stable, gets pushed away from that equilibrium state by sufficiently large perturbation. That is one example, for instance, where more advanced tools or more complicated tools of stability analysis may need to be warranted to understand the behavior of the system. And ultimately, of course, since I did not specify how this function f looks like as a nonlinear function, I only tell you here how it looks like right near an equilibrium state. Of course, you could in principle implement all kinds of crazy behavior here. So therefore, anything could happen in principle. So this is by far not an exhaustive tool that can answer all possible scenarios that can arise. And of course, there is an existing body of literature on other stability concepts of studying this.
All right, thanks.
All right. Well, let me, I see there's only 3 slides left. So let me actually move forward, closing this up, and then obviously we can have a longer discussion also following up on this. So so one thing, of course, that is intriguingly motivated by this concepts that I just highlighted as an example of how one could analyze and study microscopic models is, of course, this concept of highway traffic control. So highway traffic control, bringing the flow state in regimes that are desirable, traditionally involve ramp metering and variable speed limits. Ramp metering, for anybody who's not seen this, sometimes you have on-ramps that have traffic lights on them and limit the flow that comes in. And you could make this even feedback control, so dependent on the traffic state or just on historical averages. But the rationale is that you have that fundamental diagram, you have the critical density above any additional car that you add, reduce the flow rate, and you want to prolong on the onset of rush hour traffic the time when this happens by holding back some cars on the ramps, for example. And this has worked quite successfully up to the caveat that ramps only can store so many cars before they spill back onto the arterial roads. Variable speed limit signs, right? Many parts, especially in Europe, it's more common, but also parts in the United States have these LED speed limit signs that can be adjusted according to holding back cars that are about to run into a big congestion, for example. Those are the traditional deployed dedicated infrastructure control means. Quite expensive to set up and quite expensive also as running costs, of course. So one thing that's intriguing is as you have different levels of automation, of course, being built into the cars anyways. And when I say AV here, it doesn't need to be a fully autonomous vehicle. It can be a vehicle with some form of driving automation, right? A smart cruise control system, an adaptive cruise control system, maybe a connected system, some information exchange. But the question is, can some of these technologies be leveraged to actually do traffic flow control? There's a lot of policy questions that are unanswered about who is in charge, who owns a vehicle on the control. How would you do this? We don't care about this right now. It's just, is it feasible in principle? So if you have a low density of vehicles, say you have a ring road here, again, as an idealization of a long road of 22 vehicles, but one of them is actually a vehicle that you can control. And you can choose that function G that we had before. But the driving laws of the other cars are intrinsically unstable so that you can stop and go traffic ways. Then the question is, could I design a controller that stabilizes the traffic flow? So I'm playing this video here. Is that playing? If somebody from the admins could quickly confirm again that one can see the video.
I don't see it playing right now.
It is moving. It is moving.
Oh, it is? Okay.
So it's moving for some people? Okay. Well, let me explain what one sees. It's left and right is the same simulation. And the blue car is driving exactly the same way as the red. So it's under human control. And what you see is this dynamic instability. It started out very much like the Sugiyama ring experiment, right? So it started out uniform, but then it went into this traveling wave that you do. Now, what we do on the right, not on the left, only on the right, is at t equal to 120, we turn this blue car over to a well-designed velocity controller that is now different. So this car now drives differently. And you actually see that even though these cars still drive as before, so they still have the tendency to trying to produce instabilities, you see that this car now has something that estimates the average speed that it should go with and constantly tries to stay at that speed and not follow the temptation when this car moves a little bit away of closing the gap right away. And this turns out in this setup to be enough actually to pretty much keep the instability at bay, right? And drive the system back to a uniform flow and keep it there. And you see that this car now has traveled much further than it was here, so this has improved the throughput on the road. Now, this is well chosen. If I chose twice as many cars, this wouldn't work so well anymore at all. Yeah. So this sort of 25 cars is sort of close to the maximum of what one can do. But it really shows that even at penetration rates of 4%, you can already hope or expect that one could do a substantial prevention of stop-and-go traffic waves, for example. And given that these are actually quite detrimental to fuel consumption and increased emissions, let alone safety, this is quite an intriguing aspect and thought, because there's no dedicated infrastructure needed. These cars with these techniques will be on the roadways anyways. All you have to solve is the problem of how to implement control laws that don't just do good stuff to the vehicle itself, but do good stuff to the system around it. And that, of course, is what many of these models are really, really important for, right? In traffic flow, don't just look at your own vehicle as how can it operate well within a sea of other vehicles. Keep in mind that it affects the cars behind it and around you. And can you leverage that in a way to do good for the whole flow at large, or at least not do bad, right? So that is an intriguing perspective. And I want to highlight again that, of course, to understand some of these things before you just put it out on the road and try it, which sounds like a dangerous idea, definitely these principled models play an important role on that. Now, let me finish a little bit, of course, by stressing that in these microscopic models, you can do all kinds of stuff, and it's very easy to do. It's not that in a macroscopic model you could not do these things. There are also ways, for example, to describe moving bottlenecks in a framework where you still represent the other vehicles as a macroscopic density. But it's harder. And these things are quite easy once you have a vehicle-centric description. So, for example, you could equip every driver with their own driving law. Of course, then the question is, how the heck do you calibrate this when you have so many degrees of freedom? But in principle, you can do it. You can have space-dependent driving laws. So when there's an uphill feature, change the function, how it looks like. When there's a speed limit, of course, right? Multi-lane, of course. You need a lane switching model, but there are many out there. You can try it. Ramps, intersections, all of this can be done by certain laws. It's non-trivial to implement. There's always the calibration problem, but in principle, the framework is quite compatible and easily doable. And of course, also non-local information exchange, like connected automated vehicles. So I could have a few vehicles being read, and then this vehicle here communicates its information to that vehicle here that is has a lot of non-connected vehicles in between, but this vehicle now has non-local information about what will happen down here, which was, by the way, used in this controller. Let me go back here. This car had a control law that for safety purposes is only based on what the vehicle ahead does, but then gets an estimate sent by the other vehicles on their average speed and adjusts its desired speed accordingly. So that about the estimation problem from before. So there's some non-local information that's being used. And of course, other things, right? Vehicle to infrastructure communication and all these kind of things. People have tried a lot of things in microsimulators and come to conclusions. Of course, one problem is the predictions that you get are only as good as your calibration of the model and what you ask for. So that's always a caveat and a challenge. But in principle, these frameworks are quite powerful and neat. I want to finish with one thing that is quite important that actually came up in a research project lately where I noticed this, is that if you deal with micromodels, you have to still understand the macroscopic flow theory. For example, boundary conditions. If you take a segment of road that's not a ring road, you need to spawn vehicles at the inflow of your segment. You need to remove cars at the outflow. And in principle, it seems like, okay, of course, you just remove, it doesn't matter, right? They have left your domain, and you just spawn cars according to whatever your law is. Well, it turns out that, no, depending on what the state of your system is, it's not so easy. Why? Because ultimately, these cars still adhere to a fundamental diagram and in equilibrium, right? You have this critical density here, and below the critical density, you have forward-going information propagation that is still true in the microscopic models, forward-going with regards to the road coordinate, whereas in the congested regime, you actually have backwards-going information. So it means that you can only prescribe an inflow state if whatever inflow state you want to prescribe, and you do the Rankine-Hughes condition, so the secant line here, with what the actual state is right now, so the first car that is on the road already, gives you actually forward-going information speed. Otherwise, you're not allowed to prescribe anything. Likewise, at the outflow condition, you actually have to prescribe some conditions on how the cars leave your domain if your corresponding state is suitably congested, such that what you prescribe together with what the state actually is would actually give you a backwards going information speed. So even though you think you don't need to prescribe something, you actually have to. And if you're unaware of this, you do something and it will do something to the system, but you didn't want it, right? Or you didn't design it. So a key message is, even if you just implement these microscopic models, you have to be knowledgeable and mindful of the fundamental theorem of traffic flow. And that is a very, very important fact that I want to highlight here. Now, let me finish by providing a few more references. So on the website that what was mentioned before, there's also an implementation of a car following model called follow the leader model. That one is dynamically stable, so you will just see that the vehicles equilibrate their speeds. There's an implementation of what's called the optimal velocity model in a regime where it develops dynamic instabilities. Those are really, really simple implementations, really, really simple models. But if you're familiar with MATLAB or Octave or other things, or want to code up your Python version of this, these are some sample codes that simulate it and visualize it, but it's a few lines of code. So it's reasonably easy to understand, and I want to encourage everybody to try this out. I also want to hint, of course, there's a lot of cool stuff that's browser-based that one can use. For example, this one here, Traffic Simulation DE. Let me just see if I can actually copy right now. How do I copy here? So if I just pull up a browser here, can you see my browser? Okay, yeah. So this is just by Martin Treiber in Germany, right? And this is some car following law. And you see an on-ramp here, right? Let's maybe, and then you can turn off the on-ramp flow or adjust it accordingly. You have an inflow here, right? You can put more cars onto the road. You can put fewer cars on the road. You see that you get these features, and some of those, of course, can also be described by LWR if you like. So you can reduce stuff here, right? You can change the speed. I can make the cars wanting to go faster or having a different time gap that they want to do. I can put in a speed limit sign, right? Drag and drop. So it's very neat, but actually it gives quite a good impression already what's going on. So I want to highlight that there's resources like these kind of things that happen. Here's another link of one that's more on cities and has intersections. But one thing that's neat is, in principle, at the core of things, these are relatively simple to implement, and there's a lot of cool resources to play around with. Now, with that, I want to finish. That was the overview, by far not complete, but I hope I gave a good glimpse of what is out there in terms of models, what do people use, and what could you be wanting to look into if you have interest in working with autonomous vehicles, but want to connect it to the flow and not just what are the vehicles immediately near you do. Thank you very much.